Gravitational waves represent one of the most profound confirmations of Einstein's general theory of relativity, offering a revolutionary window into the cosmos that extends beyond traditional electromagnetic observations. These cosmic ripples in the fabric of space-time travel vast distances across the universe, carrying information about cataclysmic events that would otherwise remain invisible to astronomers. The study of gravitational wave propagation has emerged as a crucial field in modern physics, expanding our understanding of gravity, cosmology, and the fundamental nature of space and time. These waves, first proposed by Albert Einstein in 1916, have transformed from theoretical constructs to detectable phenomena, reshaping our comprehension of how information travels through the cosmos. Gravitational waves are fundamentally ripples in space-time caused by some of the most violent and energetic processes in the universe. Einstein's general theory of relativity demonstrated that massive accelerating objects, such as neutron stars or black holes orbiting each other, would disrupt space-time in such a way that waves of undulating space-time would propagate in all directions away from the source. These cosmic ripples represent distortions in the gravitational field that travel outward at the speed of light, carrying with them crucial information about their origins and providing clues to the nature of gravity itself. Unlike electromagnetic waves, gravitational waves are transient displacements in the gravitational field, generated by the relative motion of gravitating masses. The concept of gravitational waves emerged historically through several stages of theoretical development. While Einstein is most prominently associated with their prediction in 1916, earlier scientists including Oliver Heaviside in 1893 and Henri Poincaré in 1905 had proposed them as the gravitational equivalent of electromagnetic waves. This historical progression underscores how gravitational waves represent a significant departure from Newtonian mechanics, which treated gravity as having instantaneous effects everywhere. In contrast, general relativity showed that changes in gravitational fields propagate at finite speeds, just like other forms of energy. Gravitational waves propagate through space-time as oscillations that stretch and compress the fabric of the universe itself. As a gravitational wave passes through space, it causes distances between objects to increase and decrease rhythmically at a frequency equal to that of the wave. This distinctive property means that as gravitational waves propagate, they physically alter the geometry of space-time in ways that can theoretically be measured. Unlike many other physical phenomena, the magnitude of this effect decreases linearly with distance from the source, rather than following an inverse square relationship. This distinctive propagation characteristic makes gravitational waves detectable even at vast astronomical distances, provided instruments with sufficient sensitivity are available. The propagation of gravitational waves through the cosmos occurs at precisely the speed of light, approximately 186,000 miles per second, or 300,000 kilometers per second. This equality with light speed represents a fundamental prediction of general relativity that has been confirmed through observations. Gravitational waves travel unimpeded through space, largely unaffected by matter that might absorb or scatter electromagnetic radiation. This unique property gives gravitational astronomy a significant advantage over traditional methods, allowing scientists to observe phenomena that would otherwise remain hidden behind cosmic dust or dense matter. Like other waves, gravitational waves exhibit specific characteristics that define their propagation behavior. These include amplitude, the size of the wave denoted as h, frequency, how often the wave oscillates, wavelength, the distance between successive peaks, and speed. In realistic astronomical scenarios, gravitational waves reaching Earth have incredibly small amplitudes, which explains the extraordinary challenge in detecting them despite their constant passage through our planet. The relationship between these properties follows the standard wave equation, with the speed, wavelength, and frequency related by Seguin-Lef, just as with electromagnetic waves. A particularly fascinating aspect of gravitational wave propagation is their polarization states. Unlike electromagnetic waves, which have polarization states separated by 90 degrees, gravitational waves have polarization states that are 45 degrees apart. They typically manifest in two primary polarization states: plus polarization and cross polarization, which affect space differently as they propagate. In the plus polarization, space stretches and compresses along perpendicular axes, while in cross polarization, the same effect occurs but rotated by 45 degrees. This polarization property arises directly from the nature of the sources generating these waves and provides valuable information about the orientation and characteristics of cosmic events when detected. The propagation of gravitational waves begins with their generation through cataclysmic cosmic events. The strongest gravitational waves propagating through our universe originate from extraordinarily energetic phenomena such as colliding black holes, merging neutron stars, supernovae explosions, and potentially even remnants of gravitational radiation from the Big Bang. These events involve massive objects undergoing rapid acceleration or significant asymmetric mass distributions, creating disturbances in space-time that propagate outward. Binary systems consisting of two massive objects orbiting each other represent particularly efficient generators of gravitational waves, with the waves carrying away orbital energy and causing the objects to spiral increasingly closer together. In spiraling binary neutron stars represent especially powerful sources of gravitational waves as they approach coalescence. The extreme acceleration of their masses while orbiting close to one another generates strong waves that propagate throughout the universe. However, by the time these waves reach Earth after traveling astronomical distances, their effects have diminished considerably, resulting in incredibly small strains. This immense reduction in amplitude presents a fundamental challenge for detection systems, requiring instruments of extraordinary sensitivity to measure their passage. The detection of propagating gravitational waves requires remarkable technological achievements to measure minute distortions in space-time. Modern gravitational wave observatories, such as LIGO and Virgo, operate at a resolution of approximately 1 part, representing some of the most precise measurements of humanity. These facilities utilize laser interferometry to detect the minuscule stretching and compression of space as gravitational waves pass through Earth. The Japanese detector KAGRA, completed in 2019, has joined this global network, with its first joint detection with LIGO and Virgo reported in 2021. The watershed moment in gravitational wave astronomy occurred in September 2015, when LIGO detectors in Livingston, Louisiana, and Hanford, Washington, directly observed gravitational waves generated by the merger of two black holes approximately 1.3 billion light-years away. This monumental achievement, which earned Rainer Weiss, Kip Thorne, and Barry Barish the 2017 Nobel Prize in Physics, provided the first direct confirmation of gravitational waves propagating through spacetime, as Einstein had predicted a century earlier. The detection required measuring distance changes smaller than the width of a proton, highlighting the remarkable precision necessary to observe these cosmic ripples. Current research into gravitational wave propagation extends beyond Einstein's general relativity, exploring how these waves might behave under alternative theories of gravity. Recent theoretical work has examined gravitational wave propagation through the lens of geometric optic expansion and how gravitational lensing might affect wave propagation. These investigations may reveal dispersive effects, frequency-dependent propagation characteristics that could provide novel tests of cosmological gravity. Such research opens possibilities for detecting subtle deviations from general relativity, as small propagation differences would compound over cosmological distances. Scientists are particularly interested in how gravitational waves might interact with scalar or vector fields as they propagate through the universe, especially when traversing regions with gravitational lenses. While existing constraints from solar system observations and binary pulsar studies suggest that any such effects in theories like Brand's disk would be too small for current detectors to observe, the theoretical framework provides a foundation for future, more sensitive tests. As detection technology advances, these subtle propagation effects may become measurable, potentially revealing new physics beyond our current understanding. The study of gravitational wave propagation represents a profound intersection of theoretical physics, observational astronomy, and cutting-edge technology. From Einstein's mathematical prediction to the direct detections by LIGO and partner observatories, our understanding of how these cosmic ripples travel through space-time continues to expand, offering unprecedented insights into the dynamic, violent universe. As detection networks grow more sensitive and theoretical frameworks evolve, gravitational wave astronomy stands poised to reveal ever deeper secrets about cosmic events, the nature of gravity, and the fundamental fabric of space-time itself.